Ever wonder why certain materials mysteriously drawn towards magnets, while others remain indifferent? This curious occurrence, dear listeners, is a captivating subject matter known as paramagnetism. Paramagnetism, in simplest terms, can be described as an attraction to magnetic fields displayed by certain materials, an attraction that is not inherently present in all substances. This remarkable property, in fact, defines these substances. These substances are known as paramagnetic materials, demonstrating a unique magnetic response when exposed to an external magnetic field. To delve deeper, these materials under the influence of an external magnetic field align themselves in a certain manner. How fascinating is that? But remember, these are not your typical everyday magnets that attach your favorite pictures to the refrigerator. Nor are they the iron nails that help construct our homes. They are categorically different, possessing a unique form of magnetism. This form of magnetism, although not as pronounced or apparent, is subtly present. Paramagnetic materials are different, and their magnetism is a tad more subtle. At the core of this alluring force, we find the atom. The atom, a cornerstone of life as we know it, embodies a multitude of electrons. These electrons are perpetually spinning around the nucleus that sits at the atom's core, each one of them carrying a minuscule magnetic field almost invisible to the naked eye. Normally, within most ordinary, these electrons have a tendency to pair up, forming a duo. When paired, their individual magnetic fields negate each other, nullifying any magnetic effect. However, this is not always the case. Inside certain unique materials, known as paramagnetic materials, circumstances are quite different. Within these materials, some electrons remain unpaired, living solitary lives. These solitary electrons, or lone rangers, as they are often referred, lack a partner with whom to cancel out their magnetic field. As a result, when a foreign magnetic field is introduced, these electrons sense its presence and instinctively align themselves in the direction of this new field. This alignment, almost like a magnetic dance, causes the paramagnetic material to become magnetized, revealing the hidden magnetic potential. So, when an external magnetic field is applied, these unpaired electrons align themselves in the direction of the field, causing the material to become magnetized. But wait, there's a twist. This captivating phenomenon of magnetism is not something that these materials can hold on to forever. Unlike the resilient and enduring power of permanent magnets that cling steadfast to their magnetic properties, these intriguing paramagnetic materials are quite different. Their magnetic charm is fleeting, transient, and disappears as swiftly as it arrives. The very moment the external magnetic field that was triggering their magnetic abilities removed, they lose their magnetism. This fascinating process occurs due to the behavior of unpaired electrons within these materials. Once the influence of the external field is removed, these wandering electrons return to their initial, randomized orientations. This realignment creates a cancellation effect, nullifying the collective magnetism that was previously displayed. This is a unique characteristic of paramagnetic materials, one that sets them apart in the vast world of magnetism. But that's not all. There's another mesmerizing trait that these materials possess, a dependence on temperature. As the external temperature begins to rise, their magnetic prowess starts to wane. The increase in temperature results in augmented atomic vibration. This enhanced agitation disrupts the alignment of the unpaired electrons, causing them to fall out of sync. Consequently, this reduces the overall magnetism that the material can exhibit. As the temperature increases, the paramagnetism decreases. This is because higher temperatures cause greater atomic vibration, which tends to misalign the unpaired electrons, reducing the overall magnetism. So, to recap, paramagnetic materials are those that become magnetized in the presence of an external magnetic field, and conversely lose their innate magnetism when that external force is eliminated. This curious phenomenon is primarily attributed to the intriguing behavior of electrons, particularly those that are unpaired. For those who may not be familiar with the term, unpaired electrons represent a category of electrons that aren't balanced out by another electron in an opposite spin. These are the vital characters in our story of magnetization. When an external field is applied to a paramagnetic substance, these unpaired electrons, like loyal soldiers, swiftly align themselves in accordance with the direction of the field, thereby inducing magnetism. However, once the external field is removed, they revert to their random orientations, thereby causing the material to lose its magnetism. Moreover, there is an interesting caveat to this behavior. The level of paramagnetism is inversely proportional to temperature. This implies that, as the temperature escalates, the degree of induced magnetism proportionately diminishes. To put it in simpler terms, when things heat up, the magnetism cools down. Essence: it's the unpaired electrons that are the real heroes of this magnetic saga. They are the leading actors who make paramagnetic materials an exceptionally intriguing area in the realm of physics. So, the next time you come across a material that's slightly magnetic, remember, it might just be one of the paramagnetic stars of our universe. In conclusion, paramagnetism is a truly captivating and intricate phenomenon that beautifully illustrates the wonders of physics. Let's take a brief moment to revisit what we've learned. Paramagnetism is the enchanting dance of unpaired electrons aligning themselves to an external magnetic field, only to revert to their original orientations once the field is removed. This makes certain materials temporarily magnetic, a trait that is both fascinating and useful. Moreover, this phenomenon is temperature dependent, meaning that as things heat up, the magnetism cools down. This inverse relationship adds another layer of complexity and intrigue to the study of paramagnetism. Understanding paramagnetism isn't just an academic exercise. It's a glimpse into the invisible forces that shape our universe and a testament to the power and potential of unpaired electrons. It's an essential concept in physics, and its comprehension can lead to advancements in various fields from technology to healthcare. So, keep exploring, keep learning, and let the magic of paramagnetism continue to fascinate you. Remember, in the world of physics, even the smallest particles can have the most profound impact.